We're going to look at something called factoring out the GCF or greatest common factor. More on what that is later. Here's an example. When you're factoring an expression, remember that means to turn it into a product of two other things. You want to look at each term and see if there's a common factor. So do 5x and 10 have a common factor? It turns out they do. They're both divisible by 5. And watch what we can do with that fact. What I can do is I can take the number 10 and turn it into 5 times 2. Now, everybody knows that 5 times 2 is 10, but why would you want to go the other way? Why would you want to replace 10 with 5 times 2? Because by doing that, you'll notice I now have a 5 in each term. Why is that good? Well, because according to the distributive property, I can then factor out that 5, which is called the greatest common factor of the terms, and I now have a factorization. You'll notice we don't write the times sign in the final expression typically, so that's better to put it the way it is on the bottom, and that is factoring out the GCF. You can see by looking at the bottom line here that if we multiplied that together, it would in fact equal the top. And so we now have two equivalent expressions, the bottom one being factored. Let's take a look at a more complicated problem. If you look at the two terms, 20 and 12, you'll notice they're both even numbers, and therefore they both have 2 as their factor. So what I can do is I can replace 20 with 2 times 10, and I can replace 12 with 2 times 6. Why would I want to replace 20 and 12 with factored products like this? Well, because now you'll notice I have a 2 in each term. And if I have a 2 in each term, the distributive property says I can factor that 2 out. I could also rewrite this without the times sign. It means the same thing, and that's a valid factorization. Now, it's worth noting here that these two expressions are equivalent to one another. The top one is in standard form, the bottom one is in factored form, but they're both the same expression in the sense that whatever x was, they would both work out to be the same thing. However, I wouldn't necessarily consider this the best factorization. I'm not saying it's wrong. I'm saying there's a better factorization than this, and that may seem a little strange. Now let's go forward and see what that might mean. We're going to take the same problem, and we're going to make a different observation here. Earlier we observed that 20 and 12 are both divisible by 2, but aren't they both divisible by 4? And so I could then take 20 and replace it with 4 times 5, and I could take 12 and replace it with 4 times 3, which begs the question, why would I want to do this? Well, by doing this, I have a 4 in each term. And once again, the distributive property allows me then to factor out that 4. And now I have a different factorization, I'll write it without the times sign, of the same problem we did on the left side of the page. But I still wouldn't consider this the best possible factorization, more on what it means to be the best factorization later. But it is a valid factorization, and once again we have equivalent expressions here. But let's take a third look at the same problem. You'll notice that each of these terms has not only 4 as a factor, but also x as a factor. And therefore, the common factor here, which turns out to be the greatest common factor, is 4x. So what I can do is I can replace 20x squared with 4x times 5x, and I can replace 12x with 4x times 3. And as strange as this may seem, you'll notice that I now have a factor of 4x in each term. And as usual, the distributive property allows me to factor that out. And then writing that without the times sign gives me another factored expression for this very same problem that we've now factored 3 different ways. Well, in many cases, there's lots of ways to factor something. So what makes factorization better? Some better than others. So we have equivalent expressions here, as we do all over the page. But let's look at these one at a time. In the first factorization, and the first factorization and the second factorization are not complete, like the one on the right. And what makes that a complete factorization? Here's what it is. If you look at the remaining factor, and there's still a common factor in there, then it's not a complete factorization. You'll notice in the circle here that there's a common factor of 2, also a common factor of x, and 2x in fact. So because one of the factors has a common factor, then we haven't factored out the greatest common factor. It doesn't mean it's wrong, it's just not complete. On the second one, if you look at the inside factor there, you'll notice that each of those terms is a multiple of x. Each has x as a factor. And therefore, that's not a complete factorization either. This one on the right side of the screen is considered a complete factorization because if you look at the circle, there are no common factors between 5x and 3. And therefore, there's no further factorization that can be done here, and that makes the one on the right the complete factorization, and the GCF, or greatest common factor, of 4x on the outside. Let's take a look at that same problem again and see a couple of different strategies that we might go through to factor this thing. For some of you, you can simply look at the 20 and the 12, realize that 4 is the greatest common factor, notice that there's at least one x factor in every term, and then just decide to factor out of 4x and see what's left. If this seems like something that your brain is willing to do and the way you think, then you don't need to show any work whatsoever for this problem, and there's the answer. But there are very many people, and you may be one of them, who need a little bit more structure and procedure to get through this problem. So one thing you can do if you're struggling with something like this is you can factor portions of each term slowly and one step at a time. I'll show you what I mean by that. First thing you could do is put in the invisible time sign, so to speak, just to look more like a multiplication problem. And then you can start replacing things with equivalent factorizations. For example, you could replace 20 and 12 with any multiplication problem that would lead to 20 and 12. I use 10 times 2 and 6 times 2 as an example. There are other ways to do this, and there's no one single right way. But then you can look within each separate term and decide, is there anything else that's factorable? Well, 10 and 6 are both factorable, and I can replace those with multiplication problems or factorizations that are equal to them. So I replace 10 with 5 times 2 and 6 with 3 times 2. And what you do is you just keep doing this until there's no other factorizations that can be made. There's one other one that can be made here. It's a little subtle. I can replace x squared with x times x. And this essentially brings me to a point where I can no longer do any factorizations to anything in here. 5 is not factorable, 2 is not factorable, and 3 and x are not factorable. There's nothing in here that can be broken down further into a multiplication problem. Once you've gotten this far, what you want to do is identify what each term on the left and right have in common. Each term has 2 2's and an x in common. So what I can do with that is I can use the distributive property to pull out the 2 times 2 times x from each term, leaving me this product. Remember, the distributive property, when pulling the same thing out of each term, only has it once on the outside of the parentheses. And once you've pulled out every common factor from each term, you can simply remultiply together what you've pulled out. 2 times 2 times x is 4 times x. And then, once you've remultiplied things back together, you can leave off the unnecessary time signs, and you've now completed this problem.